Hi, in this video we're going to be talking about polar decomposition for 2x2 matrices. So before we get to what that is, I want to talk about some properties of vectors which are complex. So to start out with, if z is some complex number, then I want to write it as a plus bi, where a and b are both real numbers. So I is just the square root of -1. And we can, just for notational reasons, say that the real part, re of z, is equal to a, the number that doesn't have an I in it, and the imaginary part of z is equal to b. Notice that b is not an imaginary number, it's the real part, the coefficient of the I. So it's the imaginary part of z. So we can do the same thing for vectors. If we have a vector made up of a bunch of complex numbers, so here this vector is in Cn, there are n complex numbers, and we want to take the real part of that vector, well, just the definition of this is take the real part of each of the individual coordinates of the vector. And then the imaginary part of the vector is take the imaginary part of each of the coordinates of the vector. Each of these vectors here are going to be an Rn, right? All of these numbers are real, and all of these numbers are real. So one way to represent this vector z is we can say, first of all, it is just z1 through zn, just like it was before. And each of these individual numbers are their real part plus I times their imaginary part. Okay? So a plus bi, a is the real part, b is the imaginary part. Okay? And then we can split this up and say this is just a bunch of real parts made up into a vector, and then each of the imaginary parts has an I times in front of it, so we can separate that out into a vector, factor out the I times. Okay? And then we're just adding these two vectors together. And what that's saying is z can be thought of as its real part plus I times its imaginary part. So now let's look at what happens when we try to multiply matrices by complex vectors. So I'm going to use a real matrix, so all of the entries of A are real, and I'm going to state this for n by n matrices and then illustrate why this should be true by just looking at a 2x2 example. So what this says is if you take a real matrix and you multiply by the real part of a complex vector, that's the same as the real part of A just multiplied by the vector itself. And the same thing is true for the imaginary part. A times the imaginary part of a complex vector is the imaginary part of A times the complex vector. So let's do this for this particular example here. A is the 2x2 matrix, 1, 2, 0, 3, and Z is 1 minus I and 2 plus 3i. So to start out with, we have a times the real part of z is just a times 1, 2, where 1 and 2 are just the real portions of these coordinates here. And doing this matrix multiplication is going to give us 5 and 6. So the 5 comes from 1 times 1 plus 2 times 2. And the 6 comes from 0 times 1 plus 3 times 2. Okay, the imaginary part works the same way. A times the imaginary part of z is just a, and then -1, 3 is the imaginary part of z. So -1 coming from the fact that we have minus 1i, and 3 coming from the fact that we have plus 3i there. And this times this is 5, 9. Okay? And now instead of writing out this full term right here, really I just want to look at this vector a times z, and we can analyze what it is afterwards. So we have a times the vector z is going to be 1 times the first coordinate plus 2 times the second coordinate. That's this top part right here. And this bottom part is 0 times the first coordinate plus 3 times the second coordinate. And when we simplify that out, this 5 right here and this 6 right here are matching this 5 and 6. This 5 here and this 9 here are matching this 5 and 9, and that will always work out. Okay, so just to note, where does this 5 come from? This was the 1 times 1 plus 2 times 2. And where does this 5 come from? Well, this was the 1 times 1 plus 2 times 2 here, which over here was represented as 1 times this 1 right here, and then something's happening with the I, we're going to ignore that, and then 2 times this 2, something's also happening with the I, we're going to ignore that, because we only care about the real part. The i's here, so this minus I and this plus 3i that came from the imaginary parts of this, don't affect the calculation to get this 5 right here, which is why this equation works out. The same thing is going on with the imaginary case. If you look at 1 times negative 1, so the imaginary part of this, plus 2 times 3, that's exactly the imaginary part of this. Okay, and that's how we get that 5. So 1 times negative 1 plus 2 times 3 is going to be positive 5, and that's exactly what's going on right here to get this positive 5. So one way to think about why this should be true in general is to just look at this a times z is a times this representation of z that comes from over here. Z is always equal to the real part of z plus I times the imaginary part of z. And if we do this multiplication, a is linear, so a should distribute into this part and this part individually, and all of the algebra works out that I and a should commute, so the I can be pulled out here. And what's left here is we have a times the real part plus I times a times the imaginary part. But a times z can always be thought of as the real part of a times z plus I times the imaginary part of a times z. So just using this formula right here where z is replaced by a times z. And now we have these two should be equal because this is always equal to this, and this simplified down to this top one here. And we have two components of this. We have the real component and the imaginary component, and they must be equal. So what it means for two vectors to be equal, two complex vectors to be equal, is their real parts are equal and their imaginary parts are equal. Therefore, this real part must be equal to this real part, and this imaginary part must be equal to this imaginary part, which is exactly saying these two things right here. Now let's take a look at this proposition here. So A is going to be a 2 by 2 real matrix, and lambda is going to be one of its eigenvalues. Just recall that if A minus bi is an eigenvalue of lambda, and b is not 0, then the conjugate a plus bi must also be an eigenvalue. B could be negative here, so this could actually be a plus some positive number times I. I just choose to write in this format for some convenience for later on. So a minus bi is one eigenvalue that I'm choosing here to use, and we have a corresponding eigenvector v, and in general v is going to be in C2. Okay, so we take P and the real part of V, the imaginary part of V, as columns of P. And so this is a 2 by 2 matrix. So the real part of V is the real part of the top coordinate, the real part of the bottom coordinate. Imaginary part is the imaginary part of the top coordinate, imaginary part of the bottom coordinate. Okay, so P is a real matrix. And C is this matrix over here, made up of real and imaginary parts of lambda. Okay, and the proposition is that if you multiply A times P, then that's the same thing as P times C. So let's see why that works. To start out with, I'm just going to multiply A times V, and then we'll simplify this. So because V is an eigenvector with eigenvalue lambda, A times V is going to be equal to lambda times V. And lambda is A minus bi. And V can be written as the real part of V plus I times the imaginary part of V. And we're now going to look at what happens when we distribute this out. So we have a difference times a sum, and so this is going to be the first two things, A times the real part of V. And now I'm going to write these last two things because they both have an I in them, and we're going to get I squared and we're going to see that I squared is -1, so that's going to make this part the real part of our answer. And the imaginary part is going to come from a times the imaginary part over here, so a times I times the imaginary part of v, and negative b times the real part of v, so minus bi times the real part of v. Alright, so here I've just noted that I squared is -1, so I'm switching that minus sign into a plus sign, and this is all real. There's no i's left in here, so that is now the real part of AV. And these two terms have an I in them, so I'm just factoring out the I, so I have I times this thing, which is real, and so this thing, the real part of this, without the I in there, is the imaginary part of AV. Okay, so I have the real and imaginary parts of AV separated out there. Now let's look at A times P. So A times P is the same thing as A times the first column of P as the first column of our answer, and the second column of AP should be A times the second column of P. Okay, and just recall A times the real part of a vector is equal to the real part of A times the vector. So I can replace A times the real part of V with the real part of AV, which we just calculated down here. Same thing over here, A times the imaginary part of the vector is the imaginary part of A times the vector, which is this right here. Okay, so that's AP. I'm trying to show that AP is equal to PC, so now let's look at PC. Well, here we have P, and here we have the matrix C. And when you're multiplying matrices like this, remember these are columns, and so this is a 2 by 2 times a 2 by 2. The answer is going to be a 2 by 2, and I'm writing the first column as a linear combination of these two columns. So this column right here is going to distribute in A times the first plus B times the second, giving us this right here. This second column is then going to distribute in to create the second column of this 2 by 2 matrix, negative B times the first plus B times the second. So we just get that. And then we're just going to note that these things right here that we have are exactly this, and the second column is exactly that. Okay, so PC is the real part of AV, and the second column of that is the imaginary part of AV, which is exactly the answer that we got right here, A times P. So PC must be equal to AP. So that's the end of the proof, but I just want to go back. If you're uncomfortable with this step right here where we distribute this column in to create the first column of this, I've written out exactly what the details of that are. And we have our vector V is x1 plus I times y1, x2 plus I times y2. So top coordinate has subscripts 1, bottom coordinate has subscripts 2. The real part is x, the imaginary part is y. So our matrix P is the real part and the imaginary part as the two columns. And P times C is going to be this right here. So we are going to take this x1, y1, dot it with AB, and get ax1 plus by1. And for the bottom entry here in the first column, we're going to get x2, y2 dotted with AB. We're going to ax2 plus by2. Okay, and then we can take this and write it as a times this x vector plus b times this y vector. Well, the x vector is just the real part of v, right? It's the real part of this, and the y vector is the imaginary part of this. So this is a times the real part of v plus b times the imaginary part of v, which is exactly what we got right here. And similarly, this is negative b times the real part of v plus a times the imaginary part of v. So those are the details if that looked confusing. We now have these two propositions. So this first one says if b is not 0, so in other words, if lambda is actually complex and not real, then P, this matrix made up of the real and imaginary parts of V, is actually an invertible matrix. I'm going to skip the proof of this just for time's sake, but it's not too bad. Let's see. The second proposition says that C, this matrix here, made up of A's and B's, is equal to S times R, where S is a scaling matrix and R is a rotation matrix. Okay, so this is the format for a rotation matrix. I'm just saying for some theta here. I'm not specifying the theta, but I will say that if A is positive, then theta is just the arctan of B over A. And there's lots of other conditions. If A is negative, then theta is going to be pi plus the arctan of B over A. If A is equal to 0, then it's either going to be theta is positive pi over 2 or negative pi over 2, depending on the sign of B. We'll come back to that in a second. But I just want to say what these two things imply together, along with this right here. So we already know that A times P is equal to P times C. And if P is invertible, then we can write A as P times C times P inverse. Okay, so I'm just taking this equation, multiplying by P inverse on the right, both sides. Okay, and once we know that C is equal to S times R, then A will be P times S times R times P inverse. All right, so we're going to think about this similar to how we think about diagonalization, and P inverse is going to be changing our basis from the standard basis into this other basis I'm going to call the polar basis. And we can think about S and R. These can be in either order because S is a multiple of the identity and commutes with R. S and R rotate and stretch or compress once we're in that polar basis at least. And then this last matrix P is going to switch us from that polar basis back into the standard basis. So any A such that the eigenvalues are complex, so A is a 2 by 2 matrix with non-real eigenvalues, is going to be able to be written in this form. And then we can use that form to do things like raise A to powers. So let's take a look at why C is equal to a scale and times of rotation. So the scalar is going to be this square root of A squared plus B squared. And I've just written that as a matrix, but you could also just think about this as the number the square root of A squared plus B squared. And then we have this right here. So let's take a look at the picture for this. So I have a transformation C. Remember, C is this matrix AB, negative BA. And it's going to take these two standard basis vectors over here. So this is AB, and wherever AB lands, negative BA is going to be perpendicular to it. Okay. The theta that I'm getting in this right here is just going to be this angle. So I'm going to think about this red E1 rotating up and this green E2 rotating the same amount over. And then each of these are getting stretched by the same factor, which is the square root of A squared plus B squared. So these two right here have length 1, right? This is just 1, 0, and 0, 1. The distance from the origin to the end of the vector is just 1. The length of these are going to be given by the Pythagorean theorem. We can just think about this right triangle right here. I know that this distance is B, that distance is A, just because of the coordinates. And so the length is written like this, the magnitude of AB, which is the same as the length of the other one, the magnitude of negative BA, those are both just the square root of a squared plus b squared. Okay, so that's the amount we're scaling by. It's the same for each vector. And therefore we can write c as this scalar, and then here I've just factored out that amount. So this is literally the same thing as factoring a number out of the matrix that we had for c. And why is this nice? Well, I want to say that this is a rotation matrix, which is why we're doing this. So once you write these columns like this, let's just take a look at the first column here. This first column is this number and this number. So when I take these two coordinates and square them and add them together, I get this, which gives us 1. In other words, we'll say the x coordinate and the y coordinate, x squared plus y squared is equal to 1. Another way of saying that is this vector here, which is the first column, is on the unit circle. And for any point on the unit circle, you can think about the x coordinate as being cosine of theta for some theta, and the y coordinate being sine of theta for some theta. Now we can do the exact same thing for the second column, or we can just note that this is the opposite of this, and this is equal to this. So if we have cosine and sine, then the second column is just negative sine and positive cosine. So if our a coordinate here is positive, then this red vector that we have is going to form a nice right triangle with the positive x-axis. And in that case, we can just do the b coordinate divided by the a coordinate is going to be opposite divided by adjacent, which is the tangent of theta. In other words, theta is going to be the arctangent of b divided by a. Now let's look at an example. So here I have the matrix A is negative 3.06, 2.7, 5.4, and 4.5. These numbers may seem nasty, but they're chosen so that the answer looks nice so that we can analyze the answer. We're trying to find P, S, and R so that we have this. A is equal to PSR P inverse. And we want P to be invertible. We want S to be a scalar matrix, in other words, a multiple of the identity, and R to be a rotation matrix. In other words, something of this form for some theta. Alright, so lambda is going to be equal to this, and it has a corresponding eigenvector here. Just to note, there's another lambda that we could have chosen, and I just picked this one. So once we have these two things, our P matrix is just going to come from taking our vector, looking at the real part, that's our first column, so 1, negative 1, and the imaginary part, negative 2, 3, is just the imaginary part of this. So the second column is the imaginary part of our eigenvector. Okay, once we have that, then our C matrix is going to be 0.72, 0.54, coming from these two numbers right here. Notice that the sign is negative. This number in the bottom left will always be opposite of that, whereas this will have the same sign as that. Our theta is equal to the arctan of 0.72 divided by 0.54, so A over B, and this ratio is fairly nice, it's just 4/3, so I'm going to leave it like that. The decimal approximation is not a nice number, and there's no point in looking at it. So theta is an angle on this nice 3, 4, 5 triangle. So it's a right triangle, and when we want to figure out the cosine of theta, so just to note, it's the arctan of 4/3, so 4 divided by 3 is opposite over adjacent, and so that's why we get the arctan of that for this angle here, theta. And when we're looking for the cosine of the arctan of 4/3, we just need to look at this triangle and say cosine is adjacent over hypotenuse, so it's going to be 3/5, otherwise known as 0.6. And if we're looking for the sine, it's going to be opposite over hypotenuse, so 4/5, otherwise known as 0.8. So the rotation matrix looks fairly nice relative to our original matrix. And the scalar matrix is also going to be fairly nice. So 0.72 squared plus 0.54 squared is 0.81, and so you square root that and you get 0.9. So now our answer is just P times S times R, and here I've calculated P inverse just by switching the 1 and the 3 and then negating these two off-diagonal entries. So why do we care about this? Well, if we have A represented as P, S, R, P inverse, then when we raise A to, say, the nth power, we can just write n copies of this P, S, R, P inverse. And what's going to happen is, because this P inverse is right next to the P each time, they're going to cancel out. So all of these inside P inverses and P's will cancel. So this is going to cancel something there, and there's going to be something there to cancel with this one. And what we're going to be left with is one P at the very beginning, and then a bunch of S's and R's. And just remember that S and R commute, because S is just a multiple of the identity, which commutes with everything. So I'm going to move all of the S's to the left and put them right here, past the R's. And all the R's are going to stick on the right. And then at the very end, there's a P inverse. All right, and why is this nice? Why is this nicer than A to the n itself? Well, S to the n is just a multiple of the identity raised to the n, and that means I can just put the nth power on the individual real numbers that are inside of S. All right, and why is R to the n nice? So R to the n in general looks like this rotation matrix here, and when we raise it to the nth power, so R just rotates some amount, and rotating twice, in other words applying the matrix twice, just rotates again, and applying it n times will just rotate n times that angle theta. So this, raised to the nth power, is just another rotation matrix where the angle that you're rotating by is n times the original rotation angle. Let's take a closer look at what R to the n is doing to points on a plane. So to illustrate this, we're going to say that for n bigger than or equal to 0, I'm going to define the vector x sub n to be r raised to the power n times this starting vector 1, 0. So here's my starting vector. It's r to the 0 times this, in other words, just this vector itself, 1, 0. So that's my x naught. And then when I raise r to the 1 power and multiply by this, it's just going to rotate by that angle theta. So that angle theta is going to pull it up to here, and this is my x1. It's going to remain on this same circle though, because the only thing I'm doing is rotating, and that means the distance from the origin should not change. So if I wanted to apply r again, so once is here, twice is going to just rotate again, 3 times is going to rotate again, and it's going to keep doing this. It's going to go around the circle, and eventually it'll go back past x0 again. So it's going to keep going around. x8 will be over here, x9, x10, etc. So it's going to keep going around. So now we're going to do something slightly more interesting. Let's look at this new sequence yn, which is c to the n times 1, 0. So remember, c to the n is the same thing as s to the n times r to the n. So really what we're looking at is, what is this middle portion doing to the plane? Okay, and again we're going to illustrate that with a sequence, y sub n. And if we start out at this same point, so this x naught is the same thing as y naught. Then our next point is going to rotate up to where x1 is, and then it's going to scale back. So it's going to do the r rotation, and then it's going to scale by 0.9. Remember, s is this scalar 0.9. So that's going to be rotated up and then scaled back a little bit towards the origin. Okay, all of these are vectors. I'm just not putting the vector symbols on here just to avoid some clutter. Okay, y2 is going to take y1, rotate it, and then scale it by 0.9 again. So y1 rotated is going to end up right here, and then scaled by 0.9 is going to come back even more. So that's y2. Y3 is going to, these are mislabeled. Just fix that real quick. X3 and X4. Okay, so y3 is going to be over here. So rotated and then scaled back a little bit. Okay, y4 is going to come over here. Y5. Y6. And y7. Okay, so just to note, all of the xi's lied on a circle. All of the yi's will lie on a spiral. Something like that. Okay, just to note, 0.9 raised to the 7th power is a little less than 1/2, so this has come in by a factor of a little less than 1/2. So we can keep going like this, and we're just going to keep spiraling in towards the origin. Now I want to look at this matrix B here. B is P times R times P inverse, where P and R just as they were before. This is P and this is R. In other words, I'm looking at almost A, I'm just skipping this scalar matrix. So I'm going to define the sequence of vectors Zn is B to the power n times this vector. And just like raising A to high powers, if you raise this to a high power, a bunch of p's and p inverses are going to cancel each other, and b to the n is going to be p times r to the n times p inverse. Okay, here I've drawn the standard axes in black, and I've drawn these new axes, which are y equals -3/2 x and y equals -x. These are the spans of the columns of P. Okay, so 1, -1, and -2, 3. So those are drawn in purple. So we're starting with this new vector 1, -1, as opposed to the vector here that we started with was 1, 0. The idea for that is the fact that we have to multiply by this P inverse first. So because P inverse times P is the identity matrix, I know that if I take this times this, I get the identity. In other words, this times the first column of this should just be the vector 1, 0. And I want to make it so that P inverse times this vector is the vector 1, 0. So that's the setup here. And so by the time we get to this rotation matrix, I've already plugged in 1, -1, and the rotation matrix is going to take the vector 1, 0 and rotate it some amount. Okay, so here's my first point. Z0 is at 1, -1, just our starting point. And I want to plug it into here, and by the time we get to here, we're at 1, 0, then we rotate some amount, and then we multiply by the matrix P. The matrix P is going to take the point that's on the circle, so every point which is a rotation of the point 1, 0, so after this application of r to the n, is going to be some point on the circle, and then I'm going to multiply that point on the circle by P. The ellipse I've drawn poorly here is just the unit circle with the matrix transformation P applied to it. So it's the set of points which look like P times a point on the unit circle. Okay, just to note, this wasn't a mistake here. I mean, this is very hard to draw, but this does actually extend past this point by quite a bit. So this point where it reaches the axis is not the maximum y value that we obtain here. So now I'm going to attempt to plot some points, and I'm going to do this inaccurately, and that's just the way it's going to go. So the idea is, this is the first point. We apply our P inverse to get back over here. So this is P inverse of z naught, that's the same as x naught. And then we're going to apply our rotation to get us to some xi. And then to find zi, we're going to just take xi and multiply by the matrix P. So each of these points xi over here times the matrix P is going to land us on this ellipse here. And I'm just going to draw some points in. I don't really care where they are. They're definitely not going to be evenly spaced like those ones are, but where they land, not relevant. The point is there's some sort of circling around an elongated circle, in other words, an ellipse. There's some sort of rotation happening here. And when we then switch to looking at actually a to the n, we're going to get something like this. So let's create one final sequence. Oh. Let's label some stuff first. This is Z1, Z2, Z3, Z4, Z5, and Z6. Z7 should be past Z0 again, just like X7 was a little bit past X0 over there. And why not, I'll put it in. Okay, so now we want to look at what's happening with the sequence Wn defined by a to the n times our starting vector 1, negative 1. Okay, so just like x naught was equal to y naught, z naught will equal w naught. Same starting point. And because S is a scalar matrix, we can, if we want, factor it or commute it past this P and picture that scaling happening after everything else. So after we've taken our vector, moved it over here, rotated it some amount, moved it back, then we can scale it towards the origin. Okay, so it's just going to be some 0.9 raised to the power of whatever our index is. So the first one's going to be multiplied by 0.9 to get us here. We're always going towards the origin. second one's going to be something like that. So 0.81 times this. The third one's going to be something like that. Fourth one, fifth one, sixth one, and by the time we get to the seventh one, it's a little less than halfway out to Zn. So these are our Wi's. W1, W2, W3, W4, W5, and W6 and W7. Okay, these may not be exactly in the right places. I'm just trying to illustrate the idea here. Points that start on the ellipse here, after applying the matrix B to them, they're going to end up on the same ellipse. Points that start out on the ellipse, after applying the matrix A to them, will end up on an ellipse that's 0.9 times as wide, or scaled back by 0.9, so it's slightly smaller ellipse. So I'm going to attempt to draw this spiral again, and sorry for what's about to happen. Okay, so that's not very clear, but the idea is we're spiraling towards the origin again, but we're just spiraling super elongatedly. Okay, if you raise A to a high enough power and multiply by whatever vector you want, the result is going to be something that's very close to the origin. The higher the power, the closer to the origin it will be. All right, that's it. Thank you for watching.